All right, there is a starter question on there, so if you would take a look at that. So this section has, I mean, if you look at the notes, it's 2 full pages. A lot of this is a repeat of what you've seen in Math 1010. Some of it would be new. All of these are skills that you're going to use repeatedly, and these do tend to be things that students struggle with when they put all of these together, especially toward the end of this chapter when we're going to start doing some story problems involving exponentials and logarithms. If you know how they work really well, the story problems are one heck of a lot easier to understand. Even the formulas are easier to understand if you understand the basic functions of logarithmic and exponential functions. Okay. So what do we call this again? Exponential base 2. This is called exponential base 2. Is it a one-to-one function? Yes, it is. Okay. So the answer there is yes. My question for you is, how can you tell? Okay, vertical line test tells whether or not it's a function, and the horizontal line test tells whether or not it's a one-to-one function. This passes the vertical line test and the horizontal line test, so it's got to be a one-to-one function. Why is that a big deal? What does it mean about its inverse? Okay, inverse is also a function. So we've been studying exponentials for a couple days now. Exponentials are really nice. They're very useful functions. They allow us to model behavior and situations. So the last problem that we looked at was one where we were talking about barometric pressure. Barometric pressure changes with height, okay, exponentially. All right. So the next question on the starter question is, what is the two-step process for finding an inverse? Okay, what's the first step? Okay, switch X and Y. And the second step? Solve for Y. Okay, solve for Y. All right. Okay, so to get ready for this section, we're really good at working with expressions like this. These are pretty easy for everybody to understand. So these are just regular old exponential expressions. You probably first saw something like this maybe in 6th, 7th, 8th grade, somewhere in there. Okay, but this tells us how many times we use the base as a factor. So 2 to the third means we have 3 2's multiplied together, 3 factors of 2. So we end up with 8 there. This means we have 2 factors of 3, so 3 squared is 9. 4 to the negative 2, slightly more complicated because that negative in the exponent, what does that mean again? It means a word. Nope. Means reciprocal. Okay, that negative in there means reciprocal. So we're going to do the reciprocal of this expression right here. So this is going to be 1 over 4 squared. So this is going to be 1 over 16. Okay, so pretty easy here. Really familiar exponentials right here. This one's a little bit more complicated. The negative in the exponent means reciprocal. This one even a little bit more. Because if we've got a rational exponent, that means the numerator is really the exponent, and what is that denominator? What does it tell us? Somebody from my 1010 class? No. Okay, it's the root. So this really represents the square root of 16 raised to the first. So that's the square root of 16, and the square root of 16 is 4. Okay, so we are pretty familiar with stuff like this, okay, but it's a lot easier to work in this direction than it is to work in this direction right here. So, any questions about those 4 examples right there? All right, so let's take a look at this, because this is a little harder. On this one, I'm giving you the base and the answer. I'm asking you to find the exponent. So here we knew what the base was, we knew what the exponent was. We could just say, okay, that just means I have 3 2's, 2 times 2 times 2 is 8, and I'm all done. Here I've got to think about this for a second. This is kind of the opposite. You know the base and you know the answer. We're saying, what is the exponent that you put on 3 to make a 27? It would be a 3. 3 to the third equals 27. So the answer to that problem is 3. 7 to the x equals 343. Much more difficult problem. Not something that we're typically familiar with, 343. So 7 to what power? How many times do we need to multiply 7 by itself to make 343? Well, let's see. 7 times 7 is 49. Is 49 times 7 343? Yeah. It is. Okay, so the answer on this one is x equals 3. Okay, now I could have taken the time to say, hey, you know what? This side is 7 to the third. 7 to the x equals 7 to the third. It's like an exponential equation. Okay? 16 to what power equals 4? Well, that's this problem right here. Okay? If we already did this problem on this paper, it's really easy to figure that out. But if we had the one that was a bit more complicated than this, it might be a little bit difficult. So that's going to be x equals 1/2. And then how about this one? 4 to what power equals 21? Okay, now if I said this, 4 to what power equals 16? That would be 2. Correct, that would be 2. Okay, but is 21 a nice even power of 4? It's not. Okay, so that becomes a little bit more difficult. Okay. So these may be not too bad. I mean, once you get used to the way those questions are phrased. But a problem like this is much, much more difficult. In fact, it's very difficult to get an exact answer. Okay, for something like that, we're going to need a different tool. So for that, we're going to turn our attention to the relationship between exponentials and what we call logarithms. Okay, so let's take a look at the exponentials, something that you're really familiar with. There are 3 parts to an exponential. So let's make sure we're clear what they are. Okay. That's called the base. That's called the exponent. And for lack of a better word for the answer, okay, let's just call that's the number that's the answer. Okay? Now, this expression right here has a name. We call it exponential base. In this case, this would be base B. Okay? In the last section, we were talking about exponential base A. Doesn't matter what we use for the base as long as it's a positive number that's not equal to 1. Good? Okay. So the interesting part about logarithms, now everybody here I think has had 1010, okay, so you've seen logarithms before. Logarithms tend to be something that people struggle with. If you don't, that's fine, okay. Logarithms are really cool functions, okay. They are basically just like exponentials. They're just a different way to write them. So there are three parts to the expression over here. There are going to be 3 parts here. If this is exponential base B, this is going to be log base B, okay. And here's where the base goes. It goes down a little bit lower, okay? We call it subscript, and we write a little bit smaller. The exponent goes over here, and the number that this exponential is equal to goes right here. So you've got to be really familiar with how logarithms and exponentials are related. And if you'll remember a couple things, I'm convinced logarithms can be made much easier. Okay, so there are 2 things that if you remember these about logarithms, logarithms generally are a piece of cake. So the first thing is, logarithms are just another way to write exponential expressions. If you can write this exponential expression, you can write this logarithm. If you can write this logarithm, you can write that exponential expression. The key to knowing this, to knowing where to put these 3 numbers, is this. The answer to the logarithm is what? It's an exponent. The answer to a logarithm is an exponent. Okay? Now, the base is no problem here. The base shouldn't be a problem here. We say log base B, we say exponential base B. We say exponential base 5, we'd say log base 5. Stuff like that. Okay, so the base has got to go right here. The exponent has to go on the other side. The answer to a logarithm is an exponent. If you keep that in mind, you're going to be in pretty good shape. So what we want to work on is going from exponential form to logarithmic form, because sometimes it's going to be helpful to write things in logarithmic form. Sometimes it's going to be helpful to write them in exponential form. So let's take this expression right here. One that you know is true. We established this a little bit earlier. 2 to the third equals x. So we're going to write log base what? Log base 2. You want to say it that way and you want to think of it that way. Log base 2 of, okay, careful here, 8's got to go here because the exponent has to be the answer. The exponent here is the answer to the logarithm. The base is the same, and that extra number just goes right there. So Log base 2 of 8 equals 3. For this next one, this one's going to be log base what? Log base 2. What's the answer to this logarithm? Answer is the exponent, so it's going to be -5, and this is going to be 1 over 32. So log base 2 of 1/32 is -5. Here's why. Everybody watch, please. Again, it's just a question of reading these the right way. 2 to the -5 is 1 over 32. If you think of it that way, is that true? Yeah, you know that's true. Okay, the next one. This is going to be log base what? Log base 9 of 3 is the exponent of 1/2. Okay? I'm going to skip this one right here just for sake of space. If we do this right here, this is going to be log base. What's the base of the exponential? E, so that's going to be the base of our logarithm. Okay, what's the answer to the logarithm? 2. And over here we have an x. Okay? Let's do this last one. This would be log base what? Log base 10 of y equals 5. There we go. So that's going from exponential to logarithmic. Now we want to go from logarithmic to exponential. For most people, this tends to be a little bit easier. So what's the base of our exponential going to be? 6 to the second is 36. Look how much more comfortable that is than thinking of it as log base 6 of 36 is 2. Okay, 6 to the second power is 36. We're good there? Okay, let's take a look at the next one. What would the base of the exponential be? 10 to the -3. The answer to the logarithm becomes the exponent here, and this is 1 over 1,000. Okay, and that is true, right? Okay, again, let's skip down to here. Let's skip to this one right here. What's the base of the logarithm? E. Exponent is y, 31. Okay, and then the last one, you go ahead and write that. Five to the x equals 12. Okay, now I want to call your attention to this example for a reason. Everybody look up here. If you take a look at this right here, notice that this one, we've kind of got the x's and the numbers mixed. This is not our favorite expression, but what is nice about that? It explains what x is. In other words, it's an equation that's already solved. Okay? You want to know what x is? X is log base 5 of 12. Okay? It's like the solution to an equation with x in it. And we're going to see some of those later on where we're actually looking for those. Okay? Any questions? Okay, please don't forget this. This is in bold. The nice thing about being able to go from exponential to logarithmic and logarithmic to exponential is if you're having difficulty in one or the other, you can always change. So if you're having trouble in exponential form, what could you change it to? You could change it to logarithmic form. Okay, if you want to say log form, that's fine with me. Or if you're having trouble with exponent or logarithmic form, you can change it to exponential form. Okay? So going back and forth is a really valuable skill. Now, one other thing that's important to realize about logarithms is they're kind of asking a question. So if you think back several years ago, the first time you saw this expression right here, I was talking to somebody over the weekend. They're in their 50s. His wife is going back to school. She's going to the community college. She has to start out in like Math 990. She took the CPT and she said, hey, what's that funny looking check mark that's in front of these numbers? What does that mean? Okay? So the first time you see that, it looks a lot like a division symbol that everybody learns in elementary school. You say, well, what the heck does this do? Well, everybody knows now in this class that's a root symbol. Okay, that particular one, because there's no index there, there's nothing in that little crook there, we know it's a square root. Okay, well, people get used to multiplication tables and then finding, you know, they know how to square things, but square roots are kind of doing the opposite. They're going backwards. This is asking a question. This is asking, what number do you square to get 25? It's a pretty simple question. It's a little harder than saying, hey, what happens when you take 5 and square it? Well, that's just 5 times 5, so that's 25. That's easy to understand. Whenever you go in the opposite direction, it's usually a little bit more difficult. Okay? So if I said, what's the square root of 10,000? we might think for a while, but that would be 100. Okay? So finding square roots are generally more difficult. Well, once you realize that logarithms are just asking a question, it tends to be a little bit easier. So if we look at something like this, log base 2 of 32, it's asking a question. It wants to know what exponent do you put on 2 to make a 32. So remember, this answer right here is going to be an exponent. So what exponent do you put on 2 to make an 8? 3. That's the answer. What exponent do you put on 2 to make a 32? 5. What exponent do you put on 10 to make 100? 2. See how easy these are? What exponent do you put on 7 to make a 49? A 2. So log base 7 of 49 is 2. Log base 10 of 100 is 2. Okay, log base 2 of 32 is 5. Okay, let's take a look at some that are a little bit more difficult. Log base 16 of 4. Now that's the way we say it. We're saying each one of these log base whatever of the number. So log base 16 of 4. It is 1/2. Why? Because 16 to the 1/2 is 4. We looked at that problem earlier. Log base 6 of 1/6. What is it, Charles? It's going to be -1. Okay? So we say log base 6 of 1/6, but what you think is, what exponent do I put on 6 to make a 1/6? And the answer there is to make the fraction, you've got to have the negative. And to make 6 into a 6, you've got to have a 1. So it's -1. This one's kind of interesting. To make the fraction, a negative. To make the 9, a 2. Okay? Double check, is 3 to the -2, is it equal to 1/9? Yes, it is. So you can always write it in exponential form, just to double check and make sure. And what about log base 17 of 1? Very good. The answer there is 0. Remember, we went over those properties of exponents the other day. That's going to come in handy there. Okay? Any questions on that? Good review? We in good shape? Shane, how we doing? Fabulous. Thinking about your reading career? Okay. So on example 3, it says, find the inverse of y equals 2 to the x by switching x and y and then solve for y. So we're going to switch the x and y. So we're going to write x equals 2 to the y. Y is up in the exponent. We need to get it down where we can work with it. Well, you can't really square it because that would square the x. That would give us x squared. And if you squared this side, that would give us x to the 2y, which actually makes things a little bit more complicated. What's that? Okay, key here. Say that again. Okay. What form is this in? It's in exponential form. Let's write it in logarithmic form. So this is going to be log base. If this is exponential base 2, what's the base of our logarithm? That's going to be base 2. What's the answer to a logarithm? The exponent. Look at that. The y is down where we can work with it. Okay, and for lack of anything else, any place else to put it, there we go. Okay, so if the original function is 2 to the x, then its inverse is y equals log base 2 of x. Now, I'm gonna write that in a different color just so we can keep those straight, because it wants us to graph those on the same set of axes. So this is going to be y equals log base 2 of x. So if I graph the original one, this should be pretty easy. It goes through -1, 1/2, 0, 1, and 1, 2. Okay, the next convenient point that it would go through would be 2, 4. Does that sound right? Plug in a 2, raise 2 to the second, you get 4. Okay, so there's our graph. Okay, that is y equals 2 to the x. This point right here, whoops, let's do this one right here. That point right there is, let's see, 1, 2. This point right here is 0, 1, and this point is -1, 1/2. What's the horizontal asymptote? 0. Y equals 0 is our horizontal asymptote. Okay, any questions? Okay, now we're going to graph this. Tatum. Oh, if I were to plug in, whoops. If I were to plug in, a 2 into this, I get 2 squared, which is 4. If I plugged in a 3, I'd get an 8. Okay, it grows really quickly. Questions? Okay, let's graph the inverse then. What do we know about inverses as far as their graphs go? Okay, they're opposites kind of. They're reflections across the line y equal x, right? We switched all the x stuff for y stuff. So we wouldn't graph the point 1, 2. What would we graph? 2, 1. So that point right there would be 2, 1. We wouldn't graph 0, 1. We'd graph 1, 0. And we wouldn't graph negative 1, 1/2. We'd graph 1/2 comma negative 1. So 1/2 comma negative 1. So it looks like this. Oh, and look at this. This is a horizontal asymptote of y equals 0. If we switch all the x's and y's, this isn't y equals 0 anymore. It's x equals 0. So whoops, we would have a vertical asymptote here of x equals 0. Remember, we're switching all the x stuff for y stuff, all the horizontal stuff for the vertical stuff. So the graph would look something like this. So there's log base 2. And this one here is exponential base 2. You know, you did these in 1010, right? Look familiar? Okay, are there any questions? Okay, we're good? Okay, so if you know all of this stuff about an exponential, okay, which we studied in 1010, we went over that the other day. So if you know everything here about exponential base A, all we have to do is adjust that a little bit, and we know how to graph log base A. Because remember, every function makes a shape when we graph it. Exponentials make these shapes, okay, exponential growth or exponential decay, okay, and logarithms make these shapes. These have a horizontal asymptote, these have a vertical asymptote. So let's go ahead and fill in the blanks. Again, all we're doing is we're just switching the x stuff for the y stuff. So instead of having x's that are negative 1, 0, and 1, we know the y's. Instead of this y being a 1, this x is a 1. Okay? And what would this number right here be? What would this x coordinate be? This would be 1 over a, and this would be a. If this is exponential base a, this is going to be called log base a. Remember, the bases have to be the same, so same conditions there. Got to be a positive number other than 1. Okay? If the domain on a logarithm is all real numbers, what does that tell us? Sorry, if the domain on an exponential is all real numbers, from negative infinity to infinity, what does that tell us over here, the domain or the range? The range, right? Okay, because we switched the x stuff for y stuff, so that's going to be from negative infinity to infinity. And if the range on an exponential is from 0 to infinity, that's going to be the domain on the logarithm. And if exponentials have a horizontal asymptote of y equals 0, then a logarithm has a vertical asymptote of x equals 0. So notice how all the x stuff got switched for y stuff. Okay, any questions? Okay, now, I'm going to do this problem right here. You do not have to graph an exponential to be able to graph a logarithm. Okay, in fact, I'd like you to be able to just graph a logarithm from scratch, just like we graph the 3 key points for an exponential. I'd like you to know what the 3 key points are for a logarithm, but let's take a quick look. This one's going to go through 1/4, negative 1, 1/4, 0, 1, and 1/4. It's going to look like this. And it's going to have a horizontal asymptote of y equals 0. So that point is 1/4. That point is 0, 1. That's negative 1, 1/4. What's the log base 4 going to go through? 4, 1. Next. 1, 0. Okay, 1/4 about right there and down 1. So it's going to look like this. Again, do yourself a favor, draw the asymptote in first. If this has a horizontal asymptote of y equals 0, we've got a vertical asymptote of x equals 0. So it looks something like this. There's the logarithm. Notice what the domain is. Everybody watching, please? Got the graph? Okay, look up here. Remember, we've been saying all semester long, there are 3 typical functions we run into that have domain issues. Dividing by 0, not allowed. Anytime you've got division, you've got to be careful. Even roots, can't take the even root of a negative. So if we have the square root of -5 or something like that, that's not a real number. Okay, and logarithms. You cannot take the log of a negative number. It's not in the domain. Look, we don't have any points on the logarithm over here where the negatives are. Okay? So the domain for logarithms are going to be positive numbers. Okay? Again, we're talking about the parent functions. We'll talk about what we do when we transform those. Okay, any questions? Okay. Notice that on each one of these graphs there are corresponding points. This point right here was 4, 1. That corresponds here. This point right here was 1, 0. That corresponds here. And this point right here was 1/4, -1. Those are the corresponding points. All right? And the big idea here is that exponentials and logarithms that have the same base, they are inverses of each other. So you're definitely going to want to keep track of that. So if I were to say, everybody listen, if I were to say, what undoes squaring? Square root does. If I said, what undoes multiplying by 7? Dividing by 7. Okay, you know those inverses really well. You want to know these inverses just as well. So if I said, what undoes exponential base 4? Log base 4. Okay, if I said, what undoes log base 9? Exponential base 9. Okay, logs and exponentials of the same base are inverses. Okay, so there are these whole categories of inverses. Logarithms undo exponentials. Exponentials undo logarithms. Okay? Just like, I mean, really, if I said, what undoes the 597th root? Power. Okay? Okay? So there are all these categories of inverses. Here we're dealing with logarithms and exponentials. Okay? All right, now, there are 2 exponentials and logarithms that are used more often than any others. Okay? We use exponential base 10 a lot, and we use log base e a lot. Or sorry, exponential base e a lot. Okay, and because of that, we need to be able to undo those. So the inverse of exponential base e is log base e. And we say that this way. We say it literally lnx. Don't say line x or anything like that. Okay, I'll make fun of you, and then other people will make fun of you down the road. Okay, it is the inverse of exponential base e. Okay, so if you were to write that out completely, that's what it would look like. Okay, but we never write this. We write ln x. Okay, it's so important and it's used so often. If you want to use log base e, you write ln. If you want the log base e of 9, you write ln 9. Okay? The other one is what we call the common log. Okay, it's just log of x. Okay, that's how you say that, log x. Okay, and it is the inverse of exponential base 10. If you were going to write that out completely, you'd write it like this. But we never write that. Okay, and let me show you, you're actually familiar with something like this. If I write this, what does that mean? Okay, nobody has to tell you that it's a square root, right? So if somebody writes a log and doesn't write anything down here as the base, what is the base? It's base 10. Okay, just like you know that this is a 2 right here, so that it's a square root. Okay, if somebody writes an ln, the n reminds you that it's the natural number that's the base e. Okay, so keep those straight. By the way, those are the only 2 that are on your calculator. Okay, that's why they come up so often. Or they're on there because they come up so often, actually. Okay, so let's see. Let's go ahead and try and do this problem right here. Log of 5/4. Now that's a pretty ugly number. It's got a fraction in there. What base is this? Base 10. Okay, so grab your calculator. So I'm going to clear this off, and we're going to type log. And literally, you just type in 5 divided by 4, close the parentheses, hit enter. Okay, now I do need you to have your calculator because we're going to do a little bit of exploring here. Okay, this is the answer, so it's 0.0969. You know, I lopped off a bunch of decimals, but that's pretty close, right? Okay, this is, everybody listening? Because this is important. Shane? This is the answer to a logarithm. It's the answer to a logarithm. So what is it? It's an exponent. It's the exponent that goes on what? Goes on 10. So 10 to this number right here should be equal to 5/4. Or that's 1.25. So on your calculator, let's just double check and see if this works. Let's do 10 to the 0.0969. Now, if you type that in, what does your calculator give you? 12.499. Really close. Why isn't it exactly 1.25? We didn't put all the decimal places. So I think I showed you this before when we worked on some of these calculator skills. I'm going to recall log of 5/4. And then I'm going to do, everybody watch please. Okay, what's that? I did second enter a couple of times. Okay, let me flip this off for just a second so you can see these. Take a look at the log button. What's the second function of that? Exponential base 10, right? Okay, not a coincidence. Look at the square button. What's the second function of that? Square root. Why do they do that? Because they're inverses. Look at ln. Exponential base e. Okay? So I'm going to hit that button right here. I'm going to hit second. So that's going to be 10 to the, and remember, we don't have to type the whole thing again. You can get that little answer. It says A and S. It's above the negative. It's right there. Hit second negative. It'll grab the answer. Even if you have a scientific calculator, usually that's the way, especially if it's a TI. Now the cool part about this is, if we got this right, I mean, we know this was the right answer. It works perfectly. It says exactly 5/4. Does anybody remember how to change that to a fraction? Hit the math button. It's the very first thing under there. There's your 5/4. Okay, if that isn't pretty convincing, I don't know what is. Okay, are there any questions? Okay, let's just work on typing these things in. What's the base of this logarithm? Base e. Okay, we know because it's an n, natural number. So we're going to type in ln 15. You have to close the parentheses here, then you're dividing it by 3. Close the parentheses, that will compute the top, ln of 15, and then we're going to divide by 3. So go ahead and write down the answer of 0.9025. Okay? And then would you type this last one in the calculator, and when you're done, check your answer with your neighbor? Or check with Ira. She'll let you know whether or not you're right. Isn't that right? Okay. Shouldn't turn the lights off, should I? Type that in, please. Don't take an easy problem that's as simple as punching buttons on your calculator and make it hard. What do you need? What's the key to getting this right? Parentheses. So you've got to start with parentheses. ln of 100, close the parentheses, plus ln of 4. Close the parentheses twice. There's the entire top. And then I'm going to divide by the log of 7. That's the answer. Okay? 7.0896. Okay. All right. We'll pick up there tomorrow. Thank you very much.